In today's video lesson, we're going to be talking about Gibbs free energy and how we can find out whether a reaction is going to be spontaneous. So we can use standard entropy values to figure out the change in entropy in a reaction. So standard entropy is the entropy change from heating a substance from absolute zero, or 0 Kelvin, to standard temperature, 298 Kelvin. These values can be used to calculate the standard entropy change for a reaction, as I mentioned before. Now, you can find these values in section 12 of the data booklet for IB, and then use those values there. So in this example, we're being asked to calculate the standard entropy change for the reaction of 1 butene with water to form 1 butanol. And our entropy values are listed here for each of the individuals. So we have, there it is for butene, then we have water, and then we have butanol. So now we're going to plug in the values and solve. So remember, delta S is equal to the sum of the delta S's of the products minus the sum of the delta S's of the reactants. So delta S is equal to, and using those values from the last slide, 228 for the butanol minus 310 plus 189, and that's equal to negative 271 joules k mole per k mole. Now remember, this value is negative, so that tells us that there's been a decrease in entropy in this reaction. So spontaneous reactions, remember, occur without any addition of energy. So one analogy to think about would be if you start pushing a ball down a hill, so that would be meeting the activation energy requirements, it will continue down the hill without any outside force. Whereas if you start to push a ball up the hill, you have to keep pushing. You have to provide outside source of force to get the ball to the top of the hill. So non-spontaneous reactions would be like pushing a ball up a hill, and a spontaneous reaction would be like pushing a ball down a hill. You don't have to keep pushing once you've started. Now, there are certain conditions to ensure that a reaction is spontaneous. So in this example, the total entropy of the system and the surroundings must increase. So sometimes you might have a chemical reaction with a decrease in entropy, but it will still be spontaneous if the entropy of the surroundings increases and the sum of those two values is greater than 0 or equal to 0. And this would be usually due to heat loss to the environment. So here's another way of looking at that. So if you have delta H, so the enthalpy is positive and the entropy is positive, then reactions would only be spontaneous at high temperatures. If delta H is negative, so an exothermic reaction, and the delta S is positive, the reaction will be spontaneous at all temperatures. If the delta H is positive, so endothermic, and the delta S is negative, it won't be spontaneous at any temperature. And then finally, if delta H is negative, so exothermic, and it is a negative delta S, it will be spontaneous only at low temperatures. So what is Gibbs free energy? So Gibbs free energy is called free energy because it's the energy that will be released or freed up to do work. And the value of Gibbs free energy for a reaction is based upon both its enthalpy and its entropy. Both of these factors can either have a negative or a positive effect on whether or not a reaction will occur spontaneously or not. And this is how we calculate it. So delta G is equal to delta H minus T delta S. So three things will affect whether a reaction is spontaneous: the sign of delta H, whether it's negative or positive, whether it's exothermic or endothermic; the sign of delta S, whether it's an increase of entropy or a decrease of entropy; and then finally the temperature. So in this example, we're being asked to calculate the delta G for the decomposition of calcium carbonate at two different temperatures, 298 Kelvin and 1077 Kelvin. So first we need to calculate delta S. So remember, delta S is equal to the sum of the delta S's of the products minus the sum of the delta S's of the reactants. So that we will find those values in section 12 of the data booklet. So our products would be 214 plus 39, and then we subtract the delta S of the reactant, which is 88. So that is equal to 165 joules K mole. Now, we need to convert this into kilojoules. So we will divide by 1,000 because we will have to use kilojoules from our delta H's. So 0.165 kilojoules per K mole. Now we'll solve for delta G. We remember we were given delta H in the reaction. So at 298 Kelvin, delta G is equal to delta H minus T delta S. So that's equal to 178 kilojoules per mole minus 298 times 0.165, and that's equivalent to positive 129 kilojoules per mole. At 1077 Kelvin, we will solve again. Delta G is equal to delta H minus T delta S. So it's equal to 178 minus 1077 times that 0.165. Now we're going to get a negative value. It's negative 0.295 kilojoules per mole. So in the first example, because delta G is positive, it's not spontaneous. And then at the second one, because it's negative, it is spontaneous at that higher temperature. In the second one, we're to calculate the Gibbs free energy for the hydrolysis of urea. So this is the reaction there, and we're going to take some steps to solve it. So the first part, we haven't been given the delta H, so we need to use the standard heats of formation from our data booklets to solve for that, and those would also be found in section 12. So delta H is equal to, remember, the heats of formation of the products minus the heats of formation of the reactants. So it's equal to, remember, we also need to use the coefficients in these. So it's going to be equal to this. So we have negative 393.5 plus 2 times negative 46.19. And then we're going to subtract the sum of these, negative 319.2 and negative 285.9. And it's equal to negative 485.9 kilojoules minus negative 605.1 kilojoules. So it's equal to a positive 119.2 kilojoules per mole. And because that is positive, we know it's endothermic. Now we'll calculate delta S. So that's equal to the delta S's of each of those. So carbon dioxide and 2 times the ammonia minus the urea plus the water. So it's equal to 213.78 joules. Okay. Oops. Plus 2 times 192.78 minus 173.8 plus 69.95. So that's equal to 598.6 JK minus 243.8. And that's equal to 355.59 JK. Remember, we need to convert that to kilojoules, so 0.3559 kilojoules. Now we'll calculate delta G. That's equal to delta H, which is, we calculated that in the heats of formation, 119.2 kilojoules, minus T delta S, so it's going to be 298.15 Kelvin times 0.3559 kilojoules per Kelvin equals 119.2 kilojoules minus 105.8 kilojoules. So we get a positive value, so 13.1 kilojoules. And this value tells us that at room temperature, so at 298 Kelvin, urea will not spontaneously decompose in water. Now, if we apply that to biology, we remember that urea is the molecule that's formed in the liver after proteins have been deaminated and produced toxic ammonia. So we don't want urea to decompose in water because that would be really bad. We don't want urea to break apart and become ammonia again in our blood system, because then we would be poisoning ourselves.